12th, I am taking the topic explanation of the diamagnetism. How to explain this property of the metal, that is the diamagnetism. The substances which are repelled by application of magnetic field are called diamagnetic. Let us take the example of this one. Suppose we are having a bowl in which some diamagnetic material is filled. This is in absence of magnetic field. In absence of magnetic field. This is the diamagnetic material. Diamagnetic material. Now suppose we are having, this is now North Pole. Another we are having the magnet. This is now South Pole, and this bowl is placed on this magnet. Then what will happen, that this will like this. This shows that this material is being repelled by the magnetic poles, North Pole and the South Pole. So this is collected at the center. Repulsion of diamagnetic material. Diamagnetic material. Suppose we are having a rod. This is in the form of a rod. This is diamagnetic material. Diamagnetic rod. And now suppose we apply the magnetic field. Then this rod lying in this way, this will be perpendicular. This becomes perpendicular. So this is diamagnetic rod in absence of magnetic field. In absence of magnetic field. This is the rod. This is the perpendicular portion of the rod in presence of magnetic field. Diamagnetic rod in presence of magnetic field. So this becomes perpendicular. This shows that this material is being repelled by the applied magnetic field. Diamagnetism is the universal property that is possessed by all kinds of materials. So initially this was supposed that diamagnetism was all the material were the diamagnetic. Diamagnetism. Is universal property. Possessed by matter. Later some of them became the paramagnetic and ferromagnetic. Some of them became paramagnetic and ferromagnetic. So now we can understand this magnetism on the basis of electron theory. Of diamagnetism. Diamagnetism is exhibited by those materials whose atom have paired electron in their outermost orbit. When we are having the paired electron, then this electron moves. One electron is moving, suppose clockwise, and second electron will move the anti-clockwise. Both the electrons in outermost orbit move in clockwise and anti-clockwise. So now I am taking the clockwise and anti-clockwise motion, both kinds. Suppose this is an electron, this is the nucleus, and the electron is moving like this. This is now clockwise. This is the electron moving like this one. Then the current because of this will be like this. This is the current. This is the current. It means the current will be anti-clockwise because electron is negative charge. So it will have the magnetic moment in this direction. Suppose we are having the another electron and this is moving suppose clockwise, anti-clockwise like this. Like this. This is the electron moving like this one. Then the current because of this that will be in this direction. This is the current. Current. This is now anti-clockwise and this is clockwise. This is the current. So magnetic moment because of this will be in the downward direction. Just by having the right hand rule, here the right hand rule like this, magnetic moment going up, here the right hand rule, so this is not like this. So like this, then this is going just downward. Each electron produce the magnetic moment as shown in figure. Now if suppose some magnetic field is applied on it, perpendicular to the area of the magnet, and this will have the centripetal force Fc. Similarly here, this will have the centripetal force Fc, the centripetal force. Force Fc is provided by the electrostatic force of attraction by nucleus So this is towards the center. This is not center O. Now then, let magnetic field B is applied vertically downward on the electron. Then this magnetic field will give the Lorentz force. So Lorentz force due to magnetic field now this Fm is equal to minus E into V cross B. This is so much. Now then this magnetic force, the Lorentz force, this will support to one of the electron and this will not support to the another electron depending upon the motion of the electron. So this is what that, this is the electron that is moving clockwise. This is the electron. Here we are applying the magnetic field B in this way, and we have the magnetic moment initially that is so much, and this, the Lorentz force will support to this centripetal force. So this Fc and Fm both will be in the same direction. So this magnetic moment will increase. Let this is now m plus delta m, and here the electron moving clockwise, anti-clockwise, like this. This is the applied magnetic field B, this is the electron E, and this will have the force in the opposite direction. So this is now Fc and this is now Fm. So here the magnetic moment will decrease by this amount delta M. So this is M minus delta M. M minus delta M. The Lorentz force, the force Fm supports centripetal force. Centripetal force of electron. This is now figure 1, this is now figure 2. Electron as shown in figure 1. And it will increase the angular velocity. Of electron. So magnetic moment will increase. It is so, it is shown this is now m plus delta m, and it becomes m plus delta m. Now in the second figure, this magnetic force opposes the centripetal force. In figure second, the force Fm is opposite to the centripetal force. Fc. So it will decrease. The angular velocity of electron. Angular velocity of electron. The magnetic moment will decrease, magnetic moment will decrease, and becomes m minus delta m. So net increase in the magnetic moment is how much? Net magnetic moment, this is equal to m plus delta m minus delta m. So this is now equal to 2 delta m. This is the induced magnetic moment. It is induced magnetic moment. Moment opposite to applied magnetic field. Magnetic field is applied vertically downward and this increase is vertically upward. So they are opposite to each other. And as the magnetic field is switched off, the magnetic moment will be again equal to 0. As magnetic field is switched off, the net magnetic moment will be 0. So it means that initially they have no magnetic moment, but when the magnetic field is applied, then they acquire the magnetism, and that is opposite to the applied magnetic field. So they are getting the magnetism in the opposite direction of magnetic field. Thus, the diamagnetic material acquires induced magnetism opposite to applied magnetic field. Magnetic field. Now we can show that the intensity of magnetization is negative for all these such. The intensity of magnetization is negative. So now if we have this, the magnetic susceptibility, is independent of applied magnetic field and temperature. So how this we have this, suppose I take this one. This is now applied magnetic field in this direction, and here we will have the intensity of magnetization I. So this is positive, and here we will have this negative. So we have that this is I is like to this one. This shows that this susceptibility is negative. And this is independent of the applied magnetic field. If we draw the susceptibility, then we will get the graph like this. This is now susceptibility on this axis, and this we are having the H applied magnetic field. Then this is independent of this one. Similarly, if we are having this susceptibility and this is not temperature T, then this will be like this. So this shows that this chi is independent of H and chi also independent of this T. Now susceptibility. Susceptibility independent of magnetic field and the temperature, but susceptibility is negative. Susceptibility chi, this is equal to negative. As we have the relation, this relative permeability mu r is equal to 1 plus chi. And for diamagnetic material, this mu r is less than 1, so this chi is equal to negative. And also we can have the magnetic permeability of the diamagnetic material. Magnetic permeability of diamagnetic material, as we have this mu r is equal to mu upon mu naught. Mu is the magnetic permeability of the material and mu naught the magnetic permeability of the free space. So since mu r is less than 1, so this mu upon mu naught is less than 1, or this mu is less than mu naught. Magnetic permeability of this diamagnetic material is less than the magnetic permeability of the free space. Now I tell you some examples of this diamagnetic material. Examples. Now there are so many diamagnetic material in this. Water, copper, lead, mercury, and that gold, silver, and that bismuth, antimony, and then we are having this NaCl, helium, ether, hydrogen gas, helium, ether, etc. So the superconductors also, I take the example of this one, superconductors. Superconductors, etc. Now then what we have, that in case of diamagnetic material, suppose this is a diamagnetic material, the magnetic line of force is like this. This is now like this. And here, if suppose we are having to this, then the inside to this material, they are supporting to this one, but inside they are opposite, like this, as I have shown it. So these materials, this we have, suppose this is the north pole and this is now your south pole. So we can have that if we like this, then magnetic lines of force will be in this way. This is now north and this is now south, so line of force are like this. And most of them are going away from that one. This, you see that this line is going like this one, this line is going like this one, and only one line is passing through this material. So this is diamagnetic material in magnetic field. This is now your B. Also, if we have the superconductors, diamagnetic material, or we say the magnetic field line, magnetic field lines in diamagnetic. Material. Suppose we are having the superconductor. This is a superconductor. Then suppose this is the line of force. This is the superconductor. So, no magnetic line of force pass through the superconductor. Exclusion of magnetic field lines by superconductor. So this, in case of superconductor, no field line passes through this one, so there is complete exclusion of the magnetic field lines. It means there is no magnetic flux through this superconductor. So this is what is supposed that when the superconductor is highly diamagnetic, then definitely all the materials will be diamagnetic as the temperature changes. So at lowest temperature, all the materials are the diamagnetic. But as the temperature increases, then they become paramagnetic and the ferromagnetic. So this is the properties associated with the diamagnetic material, and also I have told you the explanation on the basis of the electron theory. So thank you very much.